So AI and ML is also at the application layer. I think we've seen massive talk about computer vision and audio processing and numerous different applications at the application layer, which are really driving more and more demand for bandwidth and for latency, and for different levels of quality of service throughout the network. And so this is going to continue to drive more and more demand for this bandwidth and for more reliable links. And so this really drives new bands. So we've been looking at higher millimeter wave and terahertz wave, as well as more efficient use of the low and medium bands. And so we really need better sharing strategies, better spatial reuse strategies to get there. And again, this is really a problem of complexity where we need to exploit the distribution of each sector and each device and each deployment and the resource allocation that goes into carving that up between all the users to be able to really get there. So energy efficiency is also super critical. We want very efficient machine communications on small devices, but we also want high bandwidth and high throughput devices. So really this idea of maximizing performance over difficult hardware devices that are not optimal, as well as over very difficult bands, like the high bands we've talked about. There's just a lot of demands here where we don't have nice closed ways to optimize all these problems. And so really the only way we know how to optimize these very high dimension problems is through a kind of a machine learning data-driven approach. And so I really see this end-to-end learning approach of taking the end goals of our application, whether it's the PSNR or the bit error rate or the frame error rate, and driving this through how we're encoding and decoding for our next generation cellular systems as a core enabler for how AI and ML will be a fundamental change in how we design the RAN. And so this is kind of an example of a fully learned constellation where if you're not constrained, if the spec doesn't constrain modulations to always conform to specific standards, there's a lot of online adaptation we can do to push more capacity out of our systems. And as we expand this to massive MIMO and we learn how to do massive MIMO much better and densely and more efficiently, I think there's massive opportunity here for continued improvement as these technologies evolve. And so, I think through the lens that where we're focused on immediate technologies in this area within 5G and scaling these through this evolution to 6G, I think two of the really core enablers for this are using AI and ML to rapidly make sense out of the spectrum. So if we look at spectrum sharing, if we look at security in the spectrum, anomaly and change detection or device failures or interference detection, all of these things rely on, as well as just resource allocation in the G-node B and across multiple G-node Bs on this real-time awareness of what's going on in the spectrum. How can we make the most use out of it? And so I think we've been working heavily on this problem through OmniSig, and I think that this is really a fundamental enabler for we need this real-time view of the spectrum if we want to continue to optimize the RAN and the scheduling to make the most out of it in future RAN technologies. And then also, if we look at optimizing the actual communications links, transmitters and the receiver modems in layer 1 for all these degrees of freedom, we really need to turn those transceivers into data-driven problems. And so these are some examples from our work of looking at within the 5G NR RAN, how can you look at transparent adaptation that's simply implementation specific in the current day standard, and already showing that you can significantly improve capacity and error rate performance using some of these techniques today. But I think as we evolve into 6G, we're going to start to see more standardization of the feedback and the interchange between different components in the network that allows us to work at a whole nother level where you can co-optimize between G-node Bs and UEs and other devices in the network. So I think this is really exciting for us to get to a point where we can do application, environment, and quality of service and experience aware end-to-end optimization of the communications links, which works in this really, really high dimensional problem space. So I think these are really kind of some of the really core enablers of the 6G RAN that we're certainly very focused on and most excited about. So thanks.
Thanks, Tim. That was exciting. So that whole vision of an end-to-end AIML system is indeed the key differentiator for 6G. And to tell us how to get there in terms of hardware and software, we have our next panelist is Adam Thompson, who's a senior solutions architect at NVIDIA. And he has a background in signal processing and has spent many years working on deep learning for RF, for radio frequency classification, data compression, and so on. So Adam, over to you.
Thanks, Kaushik. And thanks to everyone for listening to this panel. I think it's obviously of immense interest to all of us here in the community and defining out the standards for what future AI applications for our future communication systems will be. So I think one of the interesting things, especially as we look at the role of AI and machine learning with 6G and beyond, is to really take a good high-level survey of how AI impacted other domains as well. So if we think about the computer vision space, in 2012 we had AlexNet, which is a very simple deep learning model in the ImageNet competition that outperformed the traditional machine learning techniques. And if you peel back the layers of the onion, I think some of the stuff that's really been powering this community has been easy to use software, easy to use accelerators with this work, and development in the open. So one of the really exciting thing about these future communication systems, so 5G and 6G, is you have this open source, open architecture component where we can really have creative progress. And so, the point of my briefing here is that what we really need as a community is to come together to build really easy to use frameworks so that you don't have to be an RF engineer. You don't have to be a wireless communication engineer, and you don't necessarily have to be an expert in all of these, alphabet soup of standards that 3GPP, puts out. Love them to death, but you get confused pretty quickly. To make, adequate and appreciable change to our communication systems. And so as we look at the two fundamental needs, as I see it, is the ability, Tim, really well put up in his talk, things like spectrum sharing and increased bandwidth that comes with 5 and 6G and decreased latency and energy efficiency. So a lot of this comes down to let's do this signal processing building blocks faster than we have before that incorporate more data. So this is sort of your standard signal processing type work, the physical layer, but you're just doing more of it faster. And then obviously the emergence of AI to these these problems like spectrum collaboration, signal identification, security. And so the really nice thing that we should strive for as a software and hardware community is to not have a whole bunch of esoteric and bespoke solutions. It would be really nice if you have one framework that most people use to develop applications. And again, sort of from the computer vision deep learning community, that's predominantly these deep learning frameworks like PyTorch and TensorFlow, and the language is Python. Currently one of the accelerators are graphics cards. So I obviously am NVIDIA, so I've got a hat in the ring for graphics cards. But the nice thing to do is if we're out in the open, we can say we need ultra low nanosecond latency that can be delivered with an FPGA. But you know what? We have the same fundamental software architecture that we can use to program GPUs and to pass that data off to, to these deep learning frameworks. So Tim talked about end-to-end, deep learning approach for wireless communication systems. Mine is end-to-end for software development framework that end-to-end goal should be, on the same platform. And so, one step here, and I'm not saying this is the only solution, but one step that myself and my team are working on is realizing this idea with a software framework called QSignal. So QSignal is free and open source GPU accelerated signal processing library. And the goal here is that you can get GPU speeds, you know, and interface via online or offline signal processing for designation of your, you know, your end-to-end workflow, and then passing over to deep learning frameworks. So all of this gets GPU acceleration. You get data onto the GPU, and you keep it on the GPU so that you have end-to-end acceleration and performance here. And so again, I don't want this to be, you know, an exclusive plug to GPUs, but this is a solution like I see as we look to designing our new frameworks. Is take something that most people can get up and running relatively quickly with, and you know, make the creative engineers and developers successful with their problems.
Adam, wonderful. Thanks for telling us how to do it. So Tim told us we need to do it. You told us how to do it. And I think it's time now to move to our next panelist. John Davis joined DARPA in 2020, and he's a program manager in the Microsystems Technology Office, or MTO. And his research spans a wide variety of topics on adaptive radio frequency systems, AI, real-time processing, and so on. And this is especially important to hear from John because now that we're talking about these problems and that they have wide applicability from commercial and in the federal domain, we are interested to learn more as to how these problems can serve a wider community than just also the commercial operators. So John, over to you.
Thanks, Kaushik. The core question I'm going to consider today is, what's the role of spectrum autonomy in 6G and other future networks? As many other speakers have mentioned today, the concept of an autonomous or cognitive radio it's not a new idea. But looking forward to 6G, I think it's a great time to ask, is now the right time to adopt widespread use of cognitive radios and autonomous spectrum access approaches? I think to answer this, we really have to grapple with two questions. First, do we have the right combination of available and emerging technology across RF, compute, algorithms, and that's both at the edge and at the enterprise level. And then, do we have the right use cases and potential net end user benefits relative to all alternatives that are going to make leaping our technological and policy barriers that stand in the way of cognitive radios to make that worthwhile? Just in terms of high level benefits, why are we even considering autonomous spectrum access? I mean, the core benefit is the opportunity for much better spectral reuse. And this will be through getting access to new bands through collaborative spectrum sharing, as well as much more efficient and finer scale reuse of the bands that we already have access to. And an additional key benefit is these classes of technologies offer the potential to be much more robust to unpredicted sources of interference, particularly dynamic sources of interference. And all of these benefits are driven by having technology at edge sensors to sample the environment, and really they know best whether the details of the environment that they're operating in, and they have the ability to adapt to changing conditions at the lowest possible latencies. So DARPA has been sponsoring research in autonomous spectrum technologies for quite some time. A good recent example is the Spectrum Collaboration Challenge, or SC2, which had its final event last fall. So the goals of SC2 were really to spur innovation in collaborative autonomous management of the wireless spectrum and develop foundational technologies to the general spectrum sharing problem. And teams competed for a $2 million top prize to develop software and firmware for collaborative intelligent radio networks. And these networks interacted in the world's largest channel emulator, the Coliseum, that Kaushik mentioned earlier. And this emulator was built to host this event and is now available to support other related research. So the final SC2 event, which if you like, go check it out on YouTube, we showed enormous promise for collaborative spectrum management technologies and its ability to scale to meet demand and break congestion problems. But there are many core questions that remain, and many of these are at the intersection between technology and policy. A big one is, how do we really incentivize radios to have dynamic but fair sharing? So under SC2, we replaced conventional regulatory policies with a scoring mechanic. But what we found was scoring really drove our overall network and radio level outcomes. And sometimes this happened in unpredictable and undesirable ways. So as we're planning for the future, we need to provision for dynamism, not just in the radios themselves, but in the rule sets that we force those radios to follow. Another key issue is collaboration with incumbents. We're never going to be replacing every legacy radio. If we want to reuse bands with substantial legacy radio content, what's the right way, what's on and off limits to engage with these radios? And then finally, how do we enforce compliance and truthfulness in the good faith collaboration among autonomous radios? Cognitive radios are going to have some very complex behaviors that make it very difficult to assess whether they're behaving in a manner that we permit or even a manner that's desirable. So how we perform that oversight is going to be a key challenge going forward. Overall, there's enormous promise from these classes of technologies, and I'm really looking forward to being a part of defining those core use cases that are going to spur this technology development. If anyone in the community has interest in new research concepts that tackle these or any related problems, please feel free to reach out to me through the DARPA webpage at www.darpa.mil. Thank you.
Thanks, John. This is indeed fascinating. So you raise an interesting point that not only should the radio change, but perhaps even the rules could change, and that brings in a whole new dimension of how to play this game forward. Fascinating. So moving on to our next panelist, we are very pleased to have Professor Daniela Cabrik from UCLA, and her research interests include novel radio architecture, signal processing, machine learning, and networking techniques for cognitive radio, 5G, and massive MIMO systems. She has many awards, but let's hear from her about her vision of how all these different technologies will coexist. Daniela, please.
Okay, thank you, Kaushik. So I would like to add new points to the discussion. I think all of the previous panelists brought very important aspects. I want to recognize that we are already working on machine learning tools for 5G, and most of us actually on the panel. And I think we're kind of working from the physical layer perspective, getting IQ samples and trying to kind of advocate for data-driven approach where we can get the data and develop models for spectrum sensing, signal classification, equalization, MIMO decoding, and that's all great. And I think that 5G will embrace all these technologies, to realize. But I think that one metric that 5G will most probably fail is the latency, because and we as researchers are also kind of tackling latency from a very low level perspective. I would say we can accelerate all these, let's say, spectrum sensing or decoding techniques, but where is the real bottleneck? It's actually at the protocol and network layer kind of optimizations of routing, resource scheduling. And I think that's something that the way it's solved today is somewhat inefficient. And if you're thinking about solving, throwing, let's say, processing power, throwing it to the cloud to solve it for you, it's still a lack of memory in the system that I think learning can add, right? That it can accelerate and tell us something that we haven't really thought about before. I mean, you have this idea of knobs, but I'm not quite sure if there are knobs or there is some deeper insight. Now, one challenge that I will see for us to kind of tackle these problems is data. because again, we're working on problems where we can use SDRs and all these great test beds that we have to get IQ samples. But once you start talking about latency, I think if the data is in the hands of operators or someone who has kind of higher level view to pinpoint where this latency is coming from. So I think that's going to be the big challenge for that 6G will have to solve, and the tools that we are working on will have to kind of step up to higher layers. The second one is I think everyone kind of many people advocate that 6G will venture into new spectrum, although I agree spectrum sharing is important and lower frequencies will have to improve. But if we move to this, let's say, sub-terahertz or terahertz regions, we recognize that the density will increase, right? And the device cost will be one aspect of it. And then if you throw in now the management of this whole ultra-dense, highly directional, most probably links, then it's again that question of interference, connectivity that we have to kind of distribute, right? I think again this draws for not centralized solutions, but rather devices that can make this response to interference. I feel that interference is something that even in sub-6 we're kind of still struggling to address in the right way. But again, if we go into these higher frequencies with new channel models, with new kind of PHY technologies, how do we deal with that? And the last point I think connects the two, and that is another kind of technology that will be kind of 6G ready is the reflective arrays, right? That if we build this tiny programmable devices that we can embed in the environment, then the question will be how can devices and radios kind of interconnect with each other to optimize our network. So it enhance basically beyond just communication. And there, I think it's kind of the tricky part of, again, managing the entire complexity optimization latency. So that's kind of the convergence of the previous two problems. Thank you.
Fantastic, Daniela. Thank you very much. So I think I got a key takeaway from your talk here is that also look at the way in which you are delivering data, the protocols that support the AI functions and methods. Don't neglect them in the pursuit of just developing better and faster methods and algorithms. Network protocols are as important. That's a pretty insightful point there. So let's move on to our last speaker for today. We have John Cable, who joined InterDigital Communications in 1986. He has developed RF transceivers, baseband ASICs, and real-time software for multiple generations of wireless communication standards, from 1G all the way to 5G. So John, over to you. Very good to hear what you have to say about 6G.
Thank you, Kaushik. So my talk today, and my sort of vision for AI, I'm going to focus on, what happened to bring about the resurgence in AI and machine learning for applications. And, basically, we're all looking at machine learning as, a set of tools that will enable us to be able to achieve higher performance as we tackle, the issues and the complexity of 6G systems in the future. And ML can provide impressive performance gains over traditional approaches when our classic models are not adequate. ML allows us to extract information from the data itself. And also, there's potential for ML to help us to deal with complexity that might be more favorable than trying to tackle some of these error interface problems using classic techniques. So it's pretty well known and often said that three keys to the resurgence of artificial intelligence and machine learning based applications are the availability of large and open data sets, such as ImageNet and MNIST and so forth. These data sets were key to enabling researchers to disclose and publish their results and it was sort of a level playing field in which people can compare the results against. There were also significant advancements in deep learning models and training methods. And also we saw arriving on the scene high computational compute power. So these three keys were necessary for the resurgence of AI and machine learning. I believe these three keys will also be necessary again for AI to play a major role in 6G wireless. So I think today, based on the technology that we have in hand in terms of compute capability, in terms of our understanding of wireless channels and algorithms that are necessary to get high levels of performance out of those channels, high level of spectral efficiency. I think though we are lacking in terms of robust sets of open data sets that researchers can use and leverage as they build their algorithms. So some of the desirable attributes of wireless data sets would be that they should be open to facilitate evaluation and comparison of machine learning algorithms. They should be sophisticated and be able to support advanced complex concepts such as massive MIMO, and even beyond, such as extremely large aperture arrays and dynamic spectrum access. They should be representative of realistic deployment scenarios, such as outdoor as well as indoor scenarios, and they should be annotated with relevant metadata. And I think there's a role to be played for synthesized data sets. I think it makes sense to leverage synthesized data sets to build the initial realizations of machine learning-based approaches to solving significant problems. A recent example of a synthesized data set that has been opened is DeepMind, and it's a parameterized data set based on ray tracing that allows research in MIMO processing. But synthesized data sets can lead you into a false sense of security and maybe over-optimistic performance achievements. We really should also look at how we can open and offer to the community over-the-air-based data sets. We mentioned earlier, the Platform for Advanced Wireless Research in the US has multiple test beds that could possibly be used for interesting data generation. Maybe there's data sets that are built to complement synthesized data sets. So recently, in fact, last month in the IEEE Communications Transactions, was a paper published that was based on the DeepMind data set. And the authors demonstrated that they could actually use a sub-6 gigahertz pilot that was sent from a UE, a user equipment in the field, to select or predict the best set of MIMO weights for a millimeter wave transmission from the base station back to that UE. And it was based on, again, the DeepMind ray tracing model data set. DeepMind, that data set is based on ray tracing. It allows the user to define parameters that can identify or control the number of base stations, the number of client devices or UEs, and a number of other operating parameters with respect to the actual waveform. But it's interesting in that it, in a sense, creates a very capable and flexible data set that can consist of a tremendous amount of information. And it is done in a very concise way that really drives to the essence of the channel that is needed to actually understand and build a good performing machine learning based system. The authors presented a graph in the slides that shows what they were able to achieve with respect to this machine learning-based beam selection prediction system based on spectral efficiency on the vertical axis and SNR on the horizontal axis. And they show that they were able to converge on the upper bounds of performance using an approach like this. But again, so this is based on synthesized data, and it can lead you into a false sense of security. And as an example of why over-the-air data sets are needed, I'm referring to some work that was done at Northeastern University as part of the DARPA RFNLS project, where this project is building deep learned classifiers to detect the signatures of RF transmitters. And the confusion matrix on the left-hand side of this chart shows that, right after training, the classifier achieves very, very good accuracy. But when the researchers came back to that model and again tried to predict which one of 5 different transmitters was transmitting wirelessly in their lab, the results were quite different. And in fact, you can see quite a bit of degradation happened over just 7 days. And, it has to do with the dynamic characteristics of wireless channels. So I think the combination of synthesized data sets that are open in combination with captured data sets from over the air will help to share information, be able to drive our machine learning based approaches further and improve the quality of the results, will allow researchers to compare the results. And like we've seen with speech processing and image processing, if we have wireless, robust data sets that are open and available to the community, this will be a nice step forward to help us be able to drive progress and advancements in machine learning. So another idea, was mentioned by Kaushik in the opening. How do we drive excitement in the space? How do we get more people interested in working in this? And some of you may be aware or familiar with an online resource called Kaggle, which I think it was acquired by Google last year, but they have many, many open data sets and problems and competitions. So why not have competition for wireless machine learning in the future? I think that would help to spur the community and maybe get more interest in this space, and help to drive the whole sort of knowledge set in machine learning in combination with wireless.
John, thank you very much. And I think there's this famous quote right from Ronald Coase, a renowned British economist, who said, "If you torture data long enough, it will confess to anything." So yes, I agree with you. We do need good data sets. So there are a number of questions from the audience, and thanks for some of you to also reply in the chat. So what I'm going to do is I'm just going to pick out some of them, and if you could, even if you have replied, if you could just sort of do a one-over on them again and put forth any other insights that you may have. So one question is, and it comes up a couple of times, is how can AI/ML help in the context of, say, massive MIMO and the amount of physical layer processing that is required to solve a real network problem? And to just put this a little bit in context, you have a massive scale of a number of these radio arrays. So you're doing a trade-off in the sense that you have to complete inference in a certain time, but also your machine learning system should not introduce the latency itself as part of the inference window. So how do you balance that trade-off between, yes, go deterministic or versus go machine learning for these massive MIMO systems? Tim, you can start, and maybe we can come back to Daniela and John for further comments.
Hey, yeah, I think it's a super pertinent and immediate question in 5G, not just in 6G, but I think it will continue to grow and become a even more and more difficult problem as we move to ultra dense and ultra number of antennas. So I think if you look at massive MIMO, there's a trade-off between optimal algorithms for doing sounding estimation in the uplink, and then coming up with downlink precoding and uplink beamforming weight matrices. And on top of that, there's this problem of scheduling, resource scheduling between users that are simultaneously multi-user allocations. So you have this massive combinatorial problem of hundreds of users. You can allocate 10 or 12 at a time, and you have to rapidly get all of this channel state information for all of them and come up with optimal zero forcing or minimal interference multi-user beam patterns. So this is really hard, and in massive MIMO today, there's low complexity solutions that are being used that are not optimal, and there's very high complexity solutions that are more optimal but just aren't feasible because of the latency and the computational complexity in today's systems. And so we're going to see the dimensionality requirements growing more and more and more as we have more devices and more antennas to exploit and more users to allocate between. So I think there's this really exciting opportunity leveraging this physical layer sounding data for many, many users, and then coming up with very compact machine learning models that can be very low latency and very efficient to be able to do these operations, to really exploit all of the spatial and spectral efficiency of these dense networks, and to do so with very efficient allocation over many, many users. So I think this is exciting because you can do this today in 5G. This is just implementation. It doesn't need to be standardized. But then as you move into 6G, there's a lot of really more exciting things you can do as this can collaborate through standard protocols and interfaces throughout the network. So yeah, I mean, I think it's exciting. It's a software opportunity that exists today, and we have amazing tools to go on.
Wonderful. Thank you, Tim. That's insightful. Anyone else? Daniela, would you like to comment a little bit on that?
Yes, I mean, your question, do we go machine learning AI, or we kind of stick to our, how much do we use what we know so far, and how much we just let, I think there was a comment that, we would like for future generation to tackle these problems just with AI. And I tend to disagree. And I'll give you a recent example on exactly the problem that Tim mentioned on beam training in millimeter wave networks, which is, as he says, very difficult and time-consuming problem, right? And if you kind of look at the what machine learning, I mean, it's kind of trying to do a model compression in my mind. It's kind of trying to, very complex problem, try to have a more compact representation. And at the same time, from physics, we know that, let's say, millimeter wave channels are sparse. So there is that kind of physics sparsity that we can actually put on top of machine learning ability to compress. So actually, we've tried this kind of, I call it machine learning assisted compressive beam training, very recent paper. And that's kind of where you realize that you have to, know a little bit about wireless channel and these signal processing tools that are actually very powerful in other domains to kind of align them with machine learning as opposed to just using machine learning.
Exciting, indeed, indeed. So basically, you can't let go of the domain knowledge. That makes sense.
I think so.
John, any concluding thoughts?
No, that resonates with me. I think the domain knowledge is really necessary to really do a good job in applying machine learning and knowing how to do it and where to do it. You can't forget about the models of the channel, and you can use them to your benefit when you're building your system, and you can use them to avoid having massive amounts of data to try to use to train things. You can almost get your knowledge of how the channel performs in these channel models that we've used for many years in developing wireless systems.
Wonderful. Great. So a question comes up on, I think I'll direct this to John Davis, is what really is the difficult part of collaborative radios being able to perform an actuation step that minimizes interference. So is the problem in how to detect how much interference we are all causing together? Can we not analytically predict it if we can share this information among ourselves? And why is this an important problem? Why can't we just do beamforming and sort of just skip the areas where we are causing interference? So some more insights on interference and collaborative interference.
To answer the last part of your question first, I think beamforming can be a part of your solution. It's not an either-or proposition. It's with an AI in charge of the degrees of freedom available to your cognitive radios and cognitive radio networks. How do you really allocate those resources in a way that maximizes the availability of the network to the end user while minimizing interference across the ensemble? And the core problem is not so much detecting interference within the network itself. This is fairly straightforward to measure. It is understanding the impact of your actions to things that are external to your network. On SC2, we address this by having provisions for collaborative information sharing among networks. But really, the tech challenge there that I alluded to in my intro is the trustability of this information among various independent actors. If we're setting up a situation where an individual network is going to want to be greedy, how do we ensure that it's not saving the choicest plums for itself? So there really is an open research question on what's the best way to both share information among potentially greedy networks with a minimum amount of trust while getting the core information you need to essentially have a rising tide lift all boats. Another related challenge is again related to how you set up these scoring policies or methods for how you unpredictable environments and what truly is a policy set that is neutral and fair to all parties. Any set of policies is going to have biases, and making sure that those biases can be managed over time as part of the maintenance of the network, potentially even in real time. Another core research question.
Thank you, John. That I think clears up a lot of questions that I had already. A question that the audience is interested in is to learn, and also I think I can address this to perhaps Adam first, and then others can join in. Is we talk about heterogeneity all the time. We talk about different kinds of radios, base stations. We talked about massive MIMO. We talked about classical SDRs. John mentioned cognitive radios. So there are a number of these different kinds of hardware. What kind of software do we have that talks seamlessly to all of them, is able to obtain physical layer information and then interface, or do we have that, or is it still something in the future?
I think great question. I think this is an area of active research, and I think it's actually in terms of accelerators and software-defined radios, you have a lot of stuff that sits off of the PCIe topology in a system. And so the real engineering feat that's been done recently is really just establishing the direct path between these accelerators. So essentially what you're trying to do is the CPU is the traffic cop of data moving throughout your system. And so if you have in this case, because I know it best, then you can just say, hey, bypass that CPU and establish a direct communication between the radio and the GPU. But that's a hard engineering task, and a lot of these drivers are in the the operating system level and in, specific drivers for your NIC or for your radio, specifically. So again, I think some of the biggest challenges of designing these systems going forward is to really just put it out in the open and then have, multiple people with multiple interests. Some folks might like that, sort of conglomerated memory space with a Python API. Some people might want a C++ API. So just being flexible and working towards, a community here. That's going to be the same with all my answers. Let's build a community. Solve these problems.
Great. That's also very, inclusive message that you've said. Let's build a community. So let me ask also some of our other industry experts if they have some thoughts on this. Is that are we ready from a software point of view to interface with these different kinds of radios and hardware so that then you can do the cool machine learning things that you do? Is a software interfacing plane ready yet?
I think in a way we have a lot of that already in this form of feedback, right? So if we look at 5G systems, we have DNRS, we have SRS signals. We have all of these ground truth signals flowing back and forth in our networks. So not as much on the software side, but if we look at the protocol side and the ground truth and the data flowing in these networks, we have a lot of what we need to apply these techniques today to a lot of our networks.
So interesting thought that, but if I go back to Daniela right now, you said that we need to bring back the protocols into the discussion. But so where does the disconnect lie? Do we have it or do we not have it? Or would you want a new TCP design to deliver data sets, or perhaps to balance imbalanced data sets? So where does the protocol come in at this point? Oh, yeah, Daniela, go ahead.
If I may add, one interesting thing is we're after kind of high data rates, and I think we're pushing for that, for that. And I think we're actually realizing, very fast data rates. I think there are these other metrics that we're kind of falling behind. And then, the question is, can the network actually use this sometimes excess data rate to information that is not interested to users so that others can learn from it, right? And that's something that, 6G might try to, because if everything sits at the base station or the core network and the user is just getting the pipe and following the protocol, there's not much it can do, right? It can maybe, as I said, do physical layer stuff. But then if you kind of, through this access data, kind of get more information about what others are doing, then you can kind of do your own learning and adapt to that. So that's another thing that, so the protocols are kind of enhanced for AI adaptation, and that can kind of scale down as the networks become kind of more cognitive or more autonomous, right? But I think that building that memory in the system, right, that, to me right now, everything is kind of optimized. You start, one thing can change and you have to re-optimize everything from scratch, like you have never optimized, right? Most of the time. So that's kind of another thought on
I think I'll double down on Daniela's point. The existing protocols are structured into layers really based on human engineering, system engineering principles. And it's not at all clear that if you were to truly have an AI-based design of a complete stack, that they would necessarily divide the protocols into the same kinds of layers and abstractions that we do as domain experts. So I think cross-layer technologies that could start to open up new use cases or new performance enhancements. It's worth considering how a dynamically system engineered radio would look like. I mean, is it sufficient to have a complete stack with rigid boundaries, or do we actually want to change things like data representation up and down based on environmental measurements? Re-engineering the system, as Daniela mentions, becomes very challenging anytime there's a change. But are there classes of technologies that are up to that kind of challenge?
So the protocols of the future, they don't resemble the protocols of today. The protocols which are the AI enhanced protocols will look different, will have different boundaries, different features as they span the layers.
I think we should open our aperture to consider that. I think this is where the explosion in the potential search and optimization space becomes a major problem. You know, how do we allow things like protocols to be a problem completely intractable? That balancing act is a core question.
If I may add, like, the RTS, CTS act, I think from the kind of human engineering perspective, it was like, okay, maybe that's the most efficient because it's so compressed. But then from the learning perspective, it might not be the optimal, right? Because you might be repeatedly getting the same protocol response without actually figuring out what's going on, or it's going to take you forever to figure out why this is happening on the channel that you are on. So then the question is, can you add to that protocol some other information that can help? So that's kind of the idea. I mean, very preliminary idea on the protocols that can be more flexible to help machine learning optimize. Yeah.
Fascinating. So on that point, let me probe maybe John a little bit more on this. So no, I'm going to go to John Cable because on this. So John, you spoke about a vision where something like a physical layer, say a MIMO system, can be you can make it, you can send something on a completely different band and guide some of your decisions in a completely different band. So that could be one possible outcome of reducing some of the overhead signaling and these repetitive measurements. Since we're talking about protocols in this case, it's hard to imagine that you'll be able to collect different layers of the stack that's separated for a good reason. It's hard to collect all of these at a central location, to collect these different signaling information for example. Would you envision this, that the same processes then get, so there's a compute layer within the protocol layer itself that is acting individually on that particular layer, learning what it can and sending features somewhere else. Just trying to map what you were talking about, using signaling from one domain to another. Here we are using signaling from one layer to guide another. Any parallels that you can draw on that?
Yeah, it's not obvious actually how you can completely architect a system to utilize some of these very advanced ideas. Being able to use the signature of a signal that you receive at sub 6 gigahertz to infer what your beamforming weight should be in the in a TDD downlink for massive MIMO and millimeter wave frequencies. That is not it's not something that's easily done trying to use classic modeling techniques, but we're seeing that ideas like this are possible, leveraging deep learning technology. And this example was done using a synthesized data set. I think the next step is to actually try it on over-the-air scenarios and try to work through, what are the steps that you have to do? How do you come up with this beamforming? The beamforming vectors were determined using a traditional approach, but then that was basically the sub 6 gigahertz uplink signal was used as the label for a particular set of those weight vectors for the beamforming. So the question is, if you've done that at time 0, does that same label, that same sort of detect? And that's the question. And so, yeah, these ideas look very promising. They might not be practical in a real system. And that's we have to take these next steps to find that out, and then figure out how. Okay, what protocols do we have to put on top of that to make that all work? We probably have to have timers on beamforming vector weights. So maybe a vector weight set can only last for 5 minutes. Or maybe we need to have the top 3 weights, vector set weights, because they're good enough. We don't have to have the set, but maybe if we have the top 3 weights, yeah. So yeah, these are difficult problems, Kaushik.
Indeed. And that's why we are all here to debate and discuss them and sort of and put forth all of these outside. So we are just about to hit the time. So there is one quick feedback that I'd like from anyone who wants to contribute on this. That is there a way to reduce the footprint of you can reduce the ML footprint by using these kinds of techniques, these kinds of softwares. There's also others like say TensorFlow on these kinds of other techniques. So would that help in perhaps running it on edge devices, speeding up inference, etc.?
Yeah, I think there's a question in here in terms of machine learning and deep learning that we haven't touched on, which is this idea of complex valued neural networks. And I know there's been some active research by most of the folks, at least that I know of on this panel in this topic. And it's essentially the idea of building the software frameworks to be able to do complex value convolution and complex valued activation functions. And so as we look at inferencing and in general optimization of the network, essentially what we want to do is to reduce the numerical precision and to reduce the memory footprint overhead that within an I and a Q channel. But nevertheless, the ultimate goal would be, once the complex valued neural networks mature a bit, would be to do these similar types of optimization. So you try to go down from single precision to half precision or int4 and get results that generalize. But it's heuristic.
Yeah, I think I could add to that. I think there's really 3 classes of areas that we can look at to make these models faster and more compact. You have a lot of what Daniela and John talked about, where if we incorporate domain knowledge into the model architectures and structures, we can often come up with more compact and more efficient models. There's also a lot going on in computer vision that we can learn from, where they're coming up with much better ways to build these networks more efficiently and smaller, just with primitive operations that they're coming up with. So that general machine learning model architecture. And then finally, you do have these implementation efficiencies. So things like TinyML or TensorRT or AVX512, these are all building very efficient computer architectures that can do reduced precision and lower power inference. So you really need to leverage all 3 of those aspects to make these models really, really fast and efficient.
Wonderful. Well, thank you, Tim, very much. So we are at time at 2:55 p.m. Eastern Time. Thank you, everyone, for these insightful comments. I'll